The next thing we're going to talk about is called hydrostatic lifts. So hydro meaning water, static meaning not moving, and lifts meaning we need to raise or lower something. This is an example of a hydrostatic lift. An example of this might be a car jack where you're pushing on a small cylinder and it could lift up your car. Or you could use this phenomenon for tractors or anything else with pneumatics. So if you remember from before, pressure is going to stay the same when we're looking at the same height. And when we're doing hydrostatic lifts, the problems that we're going to encounter, all of the two sides are going to be at approximately the same height, or you can assume that the height is the same, which means that the pressure will be the same on both sides. So that means the pressure on one side is equal to the pressure on the other. And then if you remember, pressure is equal to force over area. So pressure 1 would be equal to force 1 over area 1, and pressure 2 is equal to force 2 divided by area 2. If we simplify this, we get force 1 over area 1 is equal to force 2 over area 2. And so the whole idea of this hydrostatic lifts is the pressure is the same on both sides. So here we have a hydrostatic lift problem. We have a small weight on the left and we'll have a bigger weight on the right. You put a 10 kilogram mass on a hydrostatic lift on the left side with a cross-sectional area of 1 centimeter squared. And you're going to use it to lift a weight on the other side with a cross-sectional area of 4 centimeters squared. And I want to know how much mass I can put on the right-hand side. So first things first is remember that the pressure is the same. So we have pressure 1 is force 1 over area 1, and we'll have pressure 2 is force 2 over area 2. And those two are the same because the pressures are the same. Now, when we're talking about force for this, we need the force of that 10 kilogram weight. Well, we have the mass, and if we have mass, that means we can find the gravitational force, because gravitational force is mass times gravitational field strength. So that'll give us 10 times 9.8. So that means force 1 will be 98 newtons. And the areas given in the problem, area 1 was 1 centimeter squared and area 2 was 4 centimeters squared. Now for these, the units don't matter as long as I'm paying attention and making sure that the units are the same on both sides. Because for here, I have 1 centimeter squared, and this is 4 centimeters squared. When I multiply both sides by the 4 centimeters squared to move it to the other side, the units of centimeters squared are going to cancel out. So I go ahead and solve, and I get a force 2 of 392 newtons. But if you recall, it asked for the mass. Well, in order to get mass, I'm going to say, well, this force is from the gravitational force of object 2, and that's going to be mass 2 times g, which is 9.8. So I divide both sides by 9.8, and I will get 40. So mass 2 is 40 kilograms. Now, the next thing that we need to remember is that if we squish a certain amount of volume out of one side, we're going to get the same volume of water on the other. And we could just say, oh, length times width times height for the volume of a rectangle, but it's more than that because it could also be a circle or something like that where it's a weird shape. So what we need to think about instead is think about the volume as the cross-sectional area times height. So when we're talking about a rectangle, we're looking at how much the water would be going through. So it's your cross-sectional area. So take the pipe and chop it like this, and then look at the end of the pipe and see what is the area of that pipe. Well, if it's a rectangle, it's length times width. If it's a circle, it's pi r squared. And then for both of these, you're multiplying it by whatever the height is. Now, you could think of it as height, or you could think about it as your change in y. So height or your change in y. Now, if the pipe was horizontal, this could be your change in x, depending on how far the water's moving left to right. So for this, we're going to use that for part B, it says how much will the mass on the right side go up when you push the left side down a distance of 40 millimeters? Well, the two volumes have to be the same. And we're given the cross-sectional areas of 1 centimeter squared and 4 centimeters squared. So I'm going to think about volume as the cross-sectional area times that change in height. So I get the area 1 times the change in height of 1 is equal to area 2 times the change in height of 2. Now I'm going to do something a little bit wild for this. I'm going to just keep my units. And I'm going to do this for exactly the same reason as I did before. It's because I'm going to divide by this 4 centimeters squared. And when I do that, this centimeter squared will cancel out that centimeter squared, just like the centimeters squared cancels out here and the 4 cancels out. And so what I'm left with is this 40 divided by 4, which will give me 10. And the units left are millimeters. And that'll be my change in height on the second side.